In the SN2 reaction, there are many variables that would affect the rate of the reaction. So one of them is the sterics of the electrophile. Generally, the more bulky or sterically hindered the alkyl halide is, the slower the SN2 reaction. For that reason, tertiary alkyl halides are generally considered unreactive in SN2 reactions. Secondary alkyl halides, which are shown here, are a little bit slower, but they do react in the SN2. Primary alkyl halides are great for the SN2, and methyl alkyl halides are even better. There's something called neopentyl, which is shown here. Those are a little bit slower than secondary alkyl halides. Vinyl halides and aryl halides are generally considered unreactive in the SN2 reaction for two reasons. First, the backside of the carbon to halogen bond is blocked by sterics. So in the case of a vinyl halide, this hydrogen here would block the incoming nucleophile that attacks at this angle. And as we replace this group with larger groups, let's say a methyl, that steric hindrance would be even greater. In the case of the aryl halide, we have a relatively small ring here. This is a 6-member ring. The incoming nucleophile would have to get inside of that ring to be able to attack the carbon from the backside of this bond here. In addition, the pi electrons shown here of the double bond and the pi electrons of the ring would repel the nucleophile, which has a negative charge. So for those two reasons, the vinyl and the aryl halides are generally considered unreactive in the SN2 reaction. Small cyclic alkyl halides are also fairly unreactive in the SN2. So in the case of a cyclohexyl or anything smaller, cyclopentyl, cyclobutyl, cyclopropyl, the carbon to halogen bond, at least the backside, would be blocked by the ring. So the nucleophile would have a hard time getting inside of the ring to be able to attack that carbon. Let's tackle this question, which is which of these is the most reactive in the SN2 and which is the least reactive. So when we compare these four molecules, we can see that we have a methyl bromide, we have a primary bromide, a tertiary one here, and a secondary one. In this group of four molecules, the most reactive SN2 alkyl halide would be the one that is sterically hindered the least. So in this example, A would be the most reactive because it's a methyl bromide. The least reactive would be the one that is most sterically hindered. So that would be the tertiary alkyl halide shown here. The carbon to leaving group bond strength also plays a role in the SN2 reaction rate. A few good examples are the allylic and the benzylic halides. These are excellent candidates for the SN2 reaction due to the fact that the carbon to halogen bond in both cases are fairly weak. When it comes to a carbon to chloride bond, it's roughly about 69 to 70 kcals per mole when it is allylic or benzylic. Compare that to a typical primary alkyl halide with a chlorine, which is a little bit north of 80 kcals per mole. Compare that to vinyl and aryl halides. Allylic and benzylic halides are much faster in SN2 than your typical primary alkyl halides. Meanwhile, vinyl and aryl halides are pretty much unreactive in the SN2 reaction for reasons we mentioned before. The stability of the leaving group also plays a role in the SN2 reaction rate. Generally, the best leaving groups are those that are able to stabilize the negative charge that develops after the leaving group is expelled from the alkyl halide. So this is the transition state where the nucleophile has attacked the carbon and the leaving group has partially left. Both the leaving group and the nucleophile will have a partial negative charge in the transition state, and then eventually the leaving group will be eliminated with a full negative charge on it. So the more stable that negative charge is based on the properties of the leaving group, the faster the reaction will occur. So let's take a look at how the halogens react in the SN2 reaction as a leaving group. So generally, the lower we are in the periodic table with the halogens, the faster the SN2 reaction will be. So the iodine tends to be a larger atom compared to, let's say, the fluorine. You can see that based on the bond length. So the bond length is simply related directly to the sizes of each of these halogens. Since the bond length is looking at how close the fluorine and the carbon get to each other, and if we're keeping the carbons the same in all four examples, the difference in bond length is simply due to the sizes of these individual halogens. The bond strength across these halogens when they're bonded to carbon is shown here. Notice that a carbon-fluorine bond is a very strong bond. It is about 472 kilojoules per mole. Compare that to a carbon to iodine bond, which has about half of the strength compared to a carbon-fluorine bond. As a result, the iodine is a much better leaving group. So one of the reasons we can explain this pattern is the fact that as a bigger atom is able to stabilize the negative charge on that atom as it gets expelled as a leaving group. Also, the fact that it is a weaker bond due to the fact that it's a larger atom, it also leads to the reaction being faster, since the nucleophile would have an easier time breaking the carbon to iodine bond compared to the carbon to fluorine bond. If we compare the reactivity of different leaving groups that involve atoms on the same row of the periodic table, we would have to explain their reactivity in the SN2 reaction based on electronegativity. So generally, the more electronegative the atom is, the better it is able to stabilize the negative charge on the leaving group. And so as a result, fluorine would be considered a better leaving group than, let's say, an OH group or an NH2 group. Fluorine, as we talked about in the last slide, is generally considered a poor leaving group compared to other halogens like chlorine, bromine, and iodine. Notice that hydrogen and carbon with a negative charge on it are somewhere over here. So even worse leaving groups than an OH and an NH2. And tosylate is a group that we talked about earlier, is generally considered about, depending on which study you look at, anywhere between being more reactive than a iodine or somewhere around a bromine. So there's lots of different places where it is placed in these reactivity charts. But consider tosylates fairly reactive in the SN2 as a leaving group. Water is one leaving group that we're going to encounter this semester quite often. Water would be even more reactive than a tosylate, so somewhere out here in terms of reactivity. The reason for that is compared to all of these leaving groups which have a negative charge, water it would be expelled as a neutral molecule, so it's more stable and therefore it is more reactive as a leaving group. So OH groups are terrible leaving groups, and so we generally can't do a direct substitution to eliminate an OH group, let's say on an alcohol. So if we want to do a substitution and replace the OH of an alcohol, we have to turn it first into a better leaving group. So one of the strategies that is used is reacting it with tosyl chloride, which is shown here, and a little bit of base that would turn this oxygen into a tosylate group. So essentially the oxygen attacks the sulfur, eliminates the chlorine, and now that oxygen is directly attached to the sulfur. So that's what a tosylate group looks like. That is a much better leaving group as we saw on a previous slide. So the bromide, if we wanted to use that as a nucleophile, could attack now this carbon and replace the tosylate group. And because this is an SN2 reaction, we would get inversion of stereochemistry as shown in the product here. Here is a couple of more examples of how alcohols are turned into better leaving groups before a substitution is going to occur. So for example, we can react an alcohol with thionyl chloride, SOCl2, and turn it into a chloral sulfite, which can then now be replaced by a chlorine nucleophile. So the chlorine would attack this carbon and then eliminate this bond to the oxygen, and now we would get an inversion of stereochemistry. PBr3 does basically the same thing, where the alcohol is turned into a dibromo phosphite, and now that behaves as a much better leaving group than the hydroxyl group of an alcohol. And so we can now add a nucleophile like Br negative that would attack this carbon and break this bond to the oxygen, eliminating the dibromo phosphite. As a result, we get a SN2 reaction with inversion of stereochemistry. So in this next question, we want to rank the relative reactivities of these alkyl halides or tosylates in the SN2 reaction. So we have a methyl bromide, a methyl tosylate, and an isopropyl chloride. Between these three electrophiles, we would have to rank the alkyl tosylate as the best electrophile, the most reactive. Meanwhile, the isopropyl chloride is the worst one. So this is the worst one because of the fact that we have a lot of sterics or more sterics than a methyl group and a methyl group in both of these reactants. We also have the worst leaving group among the three examples. So chlorine is a worse leaving group than bromine, and bromine is a worse group than a tosylate in general. So for that reason, this is the least reactive, and this is the most reactive. So another factor in the reactivity or the rate of an SN2 reaction is how strong of a nucleophile we're using. So generally, the best nucleophiles are those that have a negative charge. So having a negative charge means there's a lot of electron density on the nucleophile, and therefore the reaction would go faster compared to a nucleophile that had no charge on it. So for that reason, OH, the hydroxide ion with its negative charge, is a better nucleophile than water. When we look at the reaction between two possible nucleophiles, one with a negative charge, when the reaction occurs, the product would have a nucleophile attached to the carbon that contained the leaving group. So in this case, the Y group. That nucleophile, notice it has no charge in the product. That's a good thing. So we're turning a nucleophile with a negative charge into one that has no charge. So this is a more stable molecule compared to what we started with. So this is a better outcome compared to what we're seeing in the second example. A neutral nucleophile with no charge on it, like water, would be eventually converted into a product that has a positive charge on the nucleophile. So this molecule is less stable compared to our nucleophile, and so it is less likely to occur than the previous example. Another factor that would change the reactivity of a nucleophile and therefore affect the SN2 reaction rate is the resonance stabilization of a negative charge on the nucleophile. So in this example, we have an OR group, which has a negative charge on this oxygen, and then we also have an acetate ion, which has a negative charge on one of the oxygens. This negative charge on the acetate ion is actually spread over both oxygen atoms through resonance. So we can move a lone pair from this oxygen to make a double bond here, and then break this double bond to put a negative charge on this oxygen. As a result, that negative charge is spread out over two oxygen atoms. So in effect, we have half a negative charge on this oxygen and half a negative charge on the other oxygen of the acetate ion. Compare that to the OR group here, where the negative charge is concentrated on a single oxygen atom. Therefore, we have a better nucleophile in that oxygen. Electronegativity will change the reactivity of a nucleophile. So generally, the more electronegative an atom is, the tighter it holds the lone pair atoms to itself, and so it would be a poorer nucleophile compared to a less electronegative nucleophile. So a good example is the nitrogen in ammonia compared to the oxygen in water compared to the fluorine in HF. This fluorine is more electronegative than oxygen and more electronegative than the nitrogen of ammonia. So as a result, fluorine holds on to these lone pairs tighter compared to, let's say, the nitrogen here. So the nitrogen, the lone pair on it, would be more free to do reactions as a nucleophile. And so ammonia is a better nucleophile than water, and water is a better nucleophile than HF. So we previously talked about the halogens as leaving groups a few slides ago, but the halogens can also be a nucleophile in the SN2 reaction when reacted with an alkyl halide or some other alkyl group that has a leaving group. Generally, the iodine is a better nucleophile than the bromine, which is a better nucleophile than the chlorine, which is a better nucleophile than the fluorine. We can rationalize this based on atom size. So the fluorine is the smallest atom in this group, and so that means that the lone pairs are closer to the nucleus of the fluorine, and so they are held tighter, and therefore the lone pairs would have a harder time reacting as a nucleophile. The fluorine would have a harder time reacting as a nucleophile compared to the iodine, which is a very huge atom. So the lone pairs on that iodine are further away from the nucleus of the iodine, and so they're more free to do reactions, participate in reactions with electrophiles. Note that the solvent, whichever solvent we're using, sometimes will change this order of reactivity, but for our purposes, we're going to use this trend as shown here. So to summarize, nucleophiles generally will follow the same reactivity as bases, meaning the better the nucleophile, the better the base. So many molecules can either act as a nucleophile or as a base, depending on what they're reacting with. There are a few exceptions to this rule. So sometimes there are molecules that are better nucleophiles than they are bases, or vice versa. They're better bases than they are nucleophiles. But in general, good nucleophiles are also good bases. Nucleophiles generally tend to be better nucleophiles when they have a negative charge. They tend to be stronger than neutral nucleophiles. Nucleophilicity, or the strength of a nucleophile, increases down the periodic table. So the bigger the atom, like an iodine, for example, is a better nucleophile than fluorine. And nucleophile strength increases to the left of the periodic table, and this is based on electronegativity. So fluorine is a poor nucleophile compared to, let's say, the nitrogen of ammonia, because the fluorine is more electronegative, so it holds on to the lone pairs tighter, and therefore it makes it a poor nucleophile. In this table here, we see a comparison between different nucleophiles and the relative rates of these nucleophiles when it comes to reacting with methyl bromide. And so this table nicely summarizes a lot of the things that we said about the factors that influence the SN2 reaction. So for example, water is a neutral nucleophile, so it is not a great nucleophile compared to, let's say, the acetate ion, which has a negative charge on it. The acetate ion, due to the fact that there is resonance stabilization of that negative charge across these two oxygens, is not as good of a nucleophile as, let's say, the OH group or the OCH3 group. The chlorine is a worse nucleophile than iodine because of the fact that iodine is a larger atom, and so the lone pairs on the iodine are spread out further away from the nucleus, and they are more willing to react compared to the lone pairs on the chlorine. Notice the sulfur is lower on the periodic table than the oxygen. So for that reason, this is a better nucleophile than the oxygen. When it comes to the periodic table, across the periodic table, you might remember that electronegativity plays a role there. So we could do a comparison between let's say ammonia and water. Both of these are neutral nucleophiles. However, the ammonia is a better nucleophile because the nitrogen is less electronegative than oxygen, so it holds on to the lone pairs less, and so it is more willing to use that lone pair to do a reaction. All right, so this is the last factor in the reactivity of SN2 reactions. The solvent also plays a role. So generally we find that aprotic polar solvents are the best ones for SN2 reactions. Aprotic polar solvents means that they're not capable of hydrogen bonding, but they're polar, and so they're able to stabilize the transition state of the SN2 reaction. They're able to stabilize it because of the fact that they're able to sort of coordinate to the atoms that have partial charges in that transition state. So you might recall in the transition state of an SN2 reaction, we have a carbon that has a partial positive charge and is surrounded by, on one side, the leaving group, which has a partial negative charge, and on the other side, a nucleophile that's coming in with a partial negative charge. So those charges are stabilized by a polar solvent. The fact that it's aprotic also helps, and we can see that a little bit more clearly when we look at protic polar solvents. These are solvents that are capable of hydrogen bonding. They are generally are going to reduce the reactivity of generally the nucleophile. So they tend to hydrogen bond to the nucleophile, as shown here. So if you had, let's say, an alcohol, it would be hydrogen bonding to this nucleophile, which has a negative charge. And so it would add a lot of steric bulk around that nucleophile, and the nucleophile would have a hard time reaching our electrophile. Nonpolar solvents are generally are not going to help us in the SN2 reaction because they're not able to stabilize the transition state of the SN2 reaction. Here we see 4 different solvents that are considered poor solvents in the SN2 reaction. So we have methanol, water, which are poor solvents because of the fact that they can hydrogen bond. Meanwhile, hexane and benzene. These are non-polar solvents, so they're also poor uh, SN2 solvents. The solvents on the right side of the slide here are all considered fairly good SN2 solvents. So we have DMSO, we have DMF, acetonitrile, HMPA, and THF. All of these are aprotic and they're also polar, so they're great for the SN2 reaction. So as we discussed in the last slide, methanol and water are poor solvents for the SN2 reaction because they're protic. You can see that clearly here that they're the least helpful solvent for this particular substitution reaction, where an azide, which has a negative charge on one of the nitrogens, attacks this carbon and replaces the bromine. DMSO, DMF, acetonitrile, HMPA, all of them are much better solvents than water and methanol. There are many biological examples of SN2 reactions, but here's one. So norepinephrine contains a nitrogen and amino group that is a pretty good nucleophile that could react with this particular carbon that has this sulfur with a positive charge. Essentially, the sulfur and the rest of the molecule that is attached to it acts as a leaving group. So think of this as maybe like a halogen. So the nitrogen would attack this carbon, do an SN2 reaction by eliminating the sulfur and everything else attached to it. In this process, we would synthesize adrenaline after the methyl group is transferred.